Good morning, everyone. My name is Emanuel Maluleke, and I'll be talking about AI for board games. So here's an overview of what I'll be going through. Firstly, the terminology of two-person board games, then property of a good board game AI, then the Minimax search algorithm, the problems we might face with Minimax, then ways to improve the Minimax search algorithm. Okay. Firstly, a game needs players, and with board games, normally you have two players. So for the purpose of the algorithm that I'll be going through today, we'll have two players, min for minimum and max for maximum. The purpose of min is to minimize your score, and your aim is to make sure that your score stays at maximum. So in this case, you are max. Then we have the game state, which is the arrangement of the game or the pieces in the game at a given state. Then we also have the termination function, which is the function that determines when the game is over. In this case, if maybe it's chess, I don't know chess, but I would guess it's when you capture the queen. And we also have an evaluation function, which is the function you use to calculate the score. For example, you can just give any piece in the game a score of 1, so that when your piece is captured, you know that your score is decreased, and when you capture a piece of the opponent, your score will increase maybe by 1, depending on how you write your evaluation function. Okay, here are some properties of a good board game AI. First, delete. You should be able to delete irrelevant branches from the game, because the tree branch of a board game can be too large, and it can be time consuming to search for the terminating state. Then you should have a good evaluation function. For example, you can give your pieces different scores depending on how important they are. Also, if you're a chess player, you should be able to think ahead. So that's what you would like your AI to do. Okay. Now the Minimax search algorithm. Initially, you would have to generate a complete depth first search. Then you apply your evaluation function at each stage to calculate the score of your Minimax. Then you make a move that will maximize your score. So how this works is, from this game tree here, you see if white was to move up here, the score would remain the same because he still has his pieces, or he did not capture any piece from black. And if he was to move on the other side, it would be negative, because eventually black would be able to capture the white piece. So for white in this case, this is a no-go move. And for black, this would be an advantage if white was to move this way. Okay, problems you might face with the Minimax search algorithm. As I mentioned earlier, the search tree can be very large, and you might be unable to find your terminating state. On average, chess can have 35 possible moves, and often there can be 50 moves per player, and that would result to 35 to the power 100 nodes in a search tree, which is very large. Okay. Here are some ways in which you can improve your Minimax algorithm. You can try to use different evaluation functions, assigning different scores to your different pieces, depending on how important they are, and also giving higher scores to your AI if it captures an important piece of the opponent, so that you can prioritize those moves. For example, if you had a chance whereby you can capture a piece with a score of 1 or capture a piece with a score of 5, you would want your AI to choose the one with the score of 5. Also, you can use what we call an opening move database. Chess players have moves that they already know always work, initial moves. So before implementing your algorithm or running your AI algorithm, you would want to make those moves first and see if that works. You can also improve your Minimax algorithm using the alpha beta pruning, which is you eliminate branches that are irrelevant in your search tree. For example, here, this branch is irrelevant for mean because mean's goal is to minimize the score. And there's no value down here that is less than 5, which is here. And in this case, same thing, this node would be irrelevant, so it would be removed because there's no value under this tree, which is less than 6. Same here. There are many more algorithms you can search or use to create your AI. There's also what we call null move heuristics. And yeah, this is the end of my talk.